Welcome everyone to today's live update here with the latest live streams in regards to AMD and Intel performance or lack thereof, or tick or tock, whatever. We had the discovery, not only shocking discoveries that the mobile AMD 3000 are not the same Zen 2 as the desktop and enthusiast AMD 3000, but also that apparently allegedly the upcoming Intel IceLake here, the 1065G7 and such, might be higher performance than some might have expected. And I took a closer look here at this, and actually Intel doesn't have done any kind of magic there in that regards, and some of this. Are we live streaming or not? Maybe also overheating, I guess. Aging Retina MacBook Pro. I hope the stream is halfway decent. And so what have they done with, on the Linux side, of course, on the AMD side, we have seen that they have vastly increased here buffers for Zen 2, larger BTBs. Here 512 entries up from 1256, so double, and also L2 7K up from 4K, larger 1K indirect target area, 30% lower mispredict rate and such. And when we take a closer look, what magic or engineering has Intel done here for this IceLake? By the way, the internal code name is a little bit irritating to me. I can only repeat this, not a huge fan of this kind of named, geographically named ice, coffee and whatnot lakes, and on the AMD side Rome and such. Anyway, because so this is, well, Intel Core previously named IceLake, and that IceLake is previously named internal code names something else, which is here Sunny Cove. Of course, in my opinion, everything really stupid, all this naming. Just name this here 7th gen, 8th gen, that people at least know what we are talking about, because with all this naming, who knows what Palm Cove and Sunny Cove, or yeah, Sunny Cove. So here we have it, Skylake, Cabby Lake, Coffee Lake, Comet Lake. I mean, all of this is already stupid enough, but on top of this core names now, Palm Cove, which was scratched or something, Sunny Cove, whatever. Anyway, so this is 10 nanometer plus or something process, probably somewhat comparable to TSMC's, what AMD is using, their 7 nanometer. Again, this is marketing bullshit. It's like 10 nanometer or whatever anyway. So what has Intel done here, according to this wiki chip org stuff that probably is mostly accurate, I would guess. So they also write a significantly IPC uplift, Intel's self-reported average of 18%, which matches some slides I found somewhere else. So 18%, that is similar to what AMD had here. I think here this was like 15%. Here like AMD's 15% IPC. So Intel is for the most part just catching up there with the AMD side. 15, 18, whatever, also on the Intel side, right? So these numbers are internal benchmarking to the previous core, and that is even most likely not including Spectre and meltdown mitigations and such. So what you have previously lost, so basically this is just recovering from what was previously lost anyway, because this performance was already taken there by this mitigation. Also not yet clear how much hardware mitigations are they implemented in Palm Cove, Skylake, Palm Cove, Sunny Cove, of course, all those confusing names. So how did they pull off this magic? And you will probably not be surprised that this is exactly the same to what AMD has done, just larger buffers and everything, you name it. Front end 1.5 times larger micro-op cache. Micro-ops are this internal micro-ops that are decoded to and internally used, because x86 is just such a complex nightmare of an instruction set, with also variable from 1 byte to 17 bytes or something, with all these prefixes and extensions and this and that. So x86 super extremely highly complex. Of course, nobody with the same mind would want to implement this in pure hardware without microcode and such. So this is decoded to internal micro-ops for performance and such, because also not so many registers x86, especially vintage 32-bit anyway. So this is also internally working on a much larger register set. And yeah, so 1.5, so there you see the big vendors, AMD, Intel, they are also mostly kind of sort of out of ideas, I would say. Mostly this is just making everything larger, bigger and such without like a breakthrough in architecture. For this, I would say we would need much smaller, keep it small, beautiful, simple, and then massive parallel with 512 cores or something. But again, then all the software obviously needs to be rewritten. But what we are anyway doing, right, for offloading everything to the GPU and offloading everything to neural networks, if not integrated FPGAs. Then on top of this, so these are like 2,250 entries, 2.25K, up from 1,500. So this is not double. There you also see with all these billions of logic gates, you cannot just double everything. Even Intel with this vast improvements in process technology at 10 nanometer, 10 plus nanometer, they cannot just double everything. So only 1.5 times larger, wide. Then the backend, of course, all the logic units, arithmetic and such, SSE, AVX and so on, floating point, wider allocation, 5-way up from 4-way, again not double, right, not 8 from 4, but 5-way up from 4-way, 1.6 larger, retire order buffer or something, or rename order buffer. Anyway, from 352, also by the way, pro tip, always, with all the abbreviations, also always a challenge to remember all of them. So also not double, 352 up from 224 entries. A scheduler, they don't have a number here in this wiki, so up from increased from scheduler, of course, scheduling to all the logic units, multiple integer units, floating point units. So of course you need to schedule all these instructions, your instruction stream of all those instructions that are currently in flight. And the execution ports rebalanced, whatever that means. New store data port, new store AGU port, memory subsystems. So you also see here 1.8, 1.7. So nearly double. And again, in case you realize a pattern, although they try to double everything or nearly double, 1.7 point, you do not get double in performance. You get a mere 18%. So it's nearly double or 1.5 times and such. And with that, you only allow the 18% IPC upload. So much to all the billions of logic gates spent there on caches and everything. So LSU 1.8 in-flight load. So this is a load store unit. LSU for all these amazing abbreviations here. This is the same what we had in the RISC walkthrough there, MISP and RISC-V and MIPS is rendition verite, MIPS like CPU. We even still live streaming. And yeah, so in RISC you have this classically separated in load, compute and store always. And in x86 this is everything messed together. In x86 you have an instruction add, multiply and stuff with the load combined often, which you need to decode and schedule and such to this micro ops. So in-flight loads, and again, huge CPUs, right? How do we get this performance on x86? 128 entries for in-flight loads, 72 entries now for in-flight stores, and yeah, nearly doubled. And larger caches, also not doubled, right? So even Intel cannot just double everything, although they increased it vastly from 32K cache, a level 1 cache, to 48, and the L2 cache actually is doubled from 256 to 512K. Also this translation look aside buffers here, actually I did not know that. So the page tables historically on x86 there were 4K page tables. I think on 386 only, maybe, need to check. But newer processors like Pentium Pro, or whenever they introduced it, long time ago, you could have larger pages there. with 1 gigabyte, and this you need for performance for very huge mappings, for example databases, but also virtual machines. And I did not even realize they only had 16. So there you see with all the huge pages in Linux for virtualization loads and such, and increasing memory sizes, approaching terabytes of memory in high-end enthusiast systems or overpriced Mac Pros or such. I did not know that they only had 16 entries there, but this is now up so much to double here, 100 times nearly larger, from 16 to 1024 entries. And here also the regular 4K page entries, 1500 to 2048, again not even doubled, but yeah, and new entries apparently for 2 and 4 megabyte pages. Not really sure if before they didn't have entries there, no idea. Anyway, 5-level pages for virtual machine, large virtual addresses, up from before they had only, so with the 64-bit addresses on x86, but even MIPS, I think the Octane, also the R 10,000, 12,000, 14,000, I think they didn't implement the full 64-bit address range. Usually they have the highest bits not implemented, so that it made no sense. There was no memory and everything. So my point is, so first of all, Intel is not pulling off here any magic. So mostly they work the same as AMD. They have not rewritten all the microarchitecture, which would be a huge undertaking, and maybe eventually they will do for whatever. So even Intel, in all those years that they delayed this, and now finally they work on improving the performance again, even they can only pull off a lousy 18% IPC uplift here, with trying to double all the buffers, caches, in-flight, load in stores, and so on. A little bit sad, and also, yeah, it's a little bit probably a mistake of history that we are stuck with this x86 so prominently, with this overly complicated architecture. That probably is one of the reasons why Apple on the ARM side on iPad and iPhones can pull off all this performance advancements, just because first of all the ARM silicon was just so slow, so I mean they basically are just catching up, and second of all ARM of course not being as complicated or over complex as Intel's x86. Also, yeah, this stuff here, new instructions, Sunny Cove here, highly specific instructions that are really hard to use. This here is hashing, SHAR hashing, hardware acceleration, force caches to write back without flush. Yeah, AMD also something similar, read processor ID for likely multi-threading and such. And then here's the AVX 512 instructions, new instructions, vector pop count, neural network instructions, Galius field, new instructions, vector Alice Galius, view for error correction, likely, I guess, like barcode, record barcodes usually uses, but maybe even you can use this maybe theoretically in RAID systems, not sure, something like that. Bit algorithms, and again, these instructions are not automatically used. Either you need to write assembler or you need to wait for compilers to even generate this. So from just these instructions, nothing will get faster. Hey, fast short of rep move, amazing. Anyway, I hope you found this overview helpful of what is happening there on the Intel side. Welcome everyone in the audience. I hope the live stream is not too broken here today. Live streaming from around the world, I hope, with 3000 drop frames, 12%, whatever. Anyway, yeah, so no magic. Also, last note. Also, I hope you find the sites here useful if you want to read stuff like this. Also, to the vendors, stop naming this stuff, giving it funny names. Nobody's interested in Sunny Coves. Name it whatever is 10th gen core, something that we know what we are talking, because otherwise nobody knows for sure what we are talking about. Then here from this famous German blogger here, where he also got this reader letter here. There is one note. So this is hearsay. I have no insight at this. Here someone wrote allegedly, apparently, again hearsay of hearsay. I have no insider knowledge. This is just pure speculation that they write here. There are also some drawbacks that Intel obviously doesn't talk about, because who talks about drawbacks, right? The GL apparently is extremely bad, like really bad. So no idea. Well, this stuff is highly delayed, right? So probably. And also, well, if they make a profit, then only very little, but okay, don't really care about Intel's profit, whatever. But what is more interesting is that the cores allegedly do not reach very high clock rates and are highly unstable at high clock rates. Well, this is most likely also why they cannot double all the buffers, right? This is huge stacks, arrays of logic gates for all the buffers, for all the caches, for everything. And yeah, also with this increased shrinks of lithography structures there. So allegedly some people here, it wasn't me, so no idea who sends this in. Hearsay, take it with you, a fine grain of salt there. And yeah, so apparently not very high clocked, so much to Intel CPUs were possible to clock easier, higher, so maybe the next generation not as much, if this is true. And allegedly the single core turbo not very much over 4 gigahertz, and the jitter is very low, and they mostly barely reach 3.5 gigahertz, and more. No, they can't currently allegedly maybe not produce more than 4 cores per die. Again, hearsay of someone who writes something on a blog, no idea, but could be some indication that might be helpful. So for your buying decision, with this grain of salt, not really sure if it's that verse to wait for that refresh there. The AMD Ryzen, I wish AMD would have had the Ryzen 2 mobile stuff out there with a timetable on AMD that I could probably have opened before here. AMD Zen 2 3000 wiki. When you take a look on the release dates of previous refreshes here of Zen, by the way, high DPI scaling is a little bit off because the Retina MacBook Pro Linux is not happy about this right now. If you look on the refresh dates here, that the desktop here July 7th, so very soon, and mobile is not mentioned here, but when you take a look here on Zen Plus and you take this as an indication, then it's probably until the beginning of next year that there will be the mobile Zen 2 refresh, because you see here this was released September 2018, all the regular desktop stuff, August and stuff, and then mobile was then January 6th. So with this in mind, I would expect the Zen 2, and then again, this is stupid naming again. I cannot call out vendors often enough for the stupid naming, because then this would most likely be called mobile Zen 4000, which in my opinion makes no sense and is bloody stupid, but nobody asked me. And anyway, I hope you learned something and found this interesting, and this is some help for you choosing a laptop. And again, even the Zen 1 Plus there, the Zen 3000 mobile stuff, certainly plenty powerful enough for all your web browsing and text editing needs, and IDE and browser and file manager and web stuff. And yeah, new instructions always, AVX and stuff, take it with a grain of salt. You cannot immediately use them unless you have a state-of-the-art compiler, and even for a compiler it is super hard to make use of the specialized instructions and otherwise, like char, checksumming, hashing only when you open SSH